Welcome to Dynamo Reading Group Lecture 2, from mixture of expert to large-scale expert parallelism. We will cover 4 parts in this lecture. First is, why do we invent this mixture of expert and model? And then, how can we actually deploy it? Should we use tensor parallelism, expert parallelism, or wide expert parallelism? So these are the trending words, like WideEP is being recently developed by SG Lane, TensorRT LLM, that it's getting huge traction right now. And then we will discuss the challenges of WideEP and how you can leverage those challenges and find opportunities. And finally is the solutions to those challenges and let you know what tools to overcome those bottlenecks. First, what is the history of mixture of expert? This mixture of expert has been invented in the 1900s, but why did it get traction recently in 2025? In the chart on the right, it lists all of these popular models. Let's see the x-axis. It is parameters. Llama 2 has 13 billion parameters. Llama 3 has 70 billion. So it has much larger parameters. So it has good performance, but it's bulky and hard to serve on your GPU. So why mix of expert? Here, DeepSeek V2 has the same level of performance as the 70 billion model, but only has 13 billion parameters, which means you can serve it on your local GPU. Since 13 billion is, if FP8, it's only 13 gigabytes. So if you have a RTX 4090, it's very easy to serve it. If you have like 40 gigs or 24 gigs, then you can serve 13 billion, but you can't serve the 70 billion. So how does this mixture of expert achieve this magic of letting you have the same performance big models, but using only few parameters? The trick is not all parameters are activated. So in the previously, what give you performance? You need a lot of knowledge, right? A very big brain. So you need a big brain, but do you need all of the brain's computation when you solve a problem? Or you have different parts of brain for each problem? So that's how mixture of expert is invented. Say that you encountered a law-related question, then you can just activate the law part of your brain, where if you get a grammatical question, you can just activate the other parts of your brain. Therefore, you can store the entire world's knowledge in your brain, but when you actually compute a question, you can just activate only parts of it. Therefore, with the same amount of compute, you can have a big intelligence. So how many experts do you typically store? Is it just 5 experts? It turns out we usually have a huge number of experts. So DeepSeek has 256 experts, but only 8 of them are activated. So what does this 8 activated mean? Is it like one batch of token? We only have 8 experts activated, or is it per token? We will route it to only 8 experts. Does anyone know? Is it per token or per batch? It's 8.
I think it's per batch.
It's per token, I think.
Yeah, good. Thank you. It means per token. So every token we will route to 8 experts. But for one batch, so this first token might be a question about law, and it might activate it like the left 8 expert. Second, medicine will activate another 8, a set of 8 experts. So every batch you can have many GPU activated. Any questions?
Yeah, I have a quick question on the serving part, because even though there are only a fraction number of parameters activated during serving, you still need the weights to be loaded in the GPU memory, right?
Exactly.
So
go ahead.
So I guess the saving is on the computation part, where during serving you could save a lot of computation, I guess, as well during the training part, right?
Yes. Computation is, so you have more parameter with the same number of compute.
Yeah, I actually have another quick question. Does it going to matter how much does it impact on the scaling of the attention? Because we know if it's full attention, it's going to be quadratic, right? So the longer the sequence gets, I guess the more memory it's going to need. And then is MOE going to require much less of KB cache, or it doesn't matter for this in this case?
Yeah, good question. Yeah, I will. Can I answer that in the next few slides?
Yeah, of course.
Yeah, that's a great question. So this gives you a feeling of how many experts you would need. So 256, that's a lot of experts. Right. So why not just 6 experts, 8 experts, but this number of experts? So DeepSeek, they did an evaluation study using either 16 expert or 63 expert, and it turns out that the more expert you have, the higher performance you get. This is 33 expert, this is 16 expert. And why more experts are better? So given the same number of parameters in total. So this is the idea of fine-grained expert. So for the 16 expert, each expert will be big. Whereas if you have 63 expert, each one will be very fine-grained. and that will let you specialize more in one domain of knowledge, such as this expert can detect a noun, the other detected verbs, and in the training, it's easier to train a specialized expert than one expert that both knows noun and both knows verbs. So that's why we have fine-grained expert. So now we have the idea of having a lot of experts. How can we implement it in real world? So because we have many experts, so one dense neural network before, say, can be split into 4 experts. But with mixture of expert, we have additional experts, like 2, 5, 6 expert, and only 8 of them are activated. So we have suddenly a ton more weight matrices. Therefore, it's a huge pressure on the GPU memory. So what happens? What are some solutions to deal with the increasing memory if it cannot fit on one GPU? What are some parallelism strategies we can think of? So if the weights can't fit on one GPU, a natural idea is to use tensor parallelism, split this FFN, this mixture of expert feed forward neural network, into different GPUs. Yeah, this one GPU can only fit, say, 8 expert, but now you have 2, 5, 6 expert. You will need multiple GPUs to host them. So tensor parallelism is the original method proposed in the NVIDIA paper called Megatron. Say you have 8 experts here, and you have 2 GPUs. Each expert matrix, you can cut it in half. So GPU 1 will have all the 8 experts, but half of each. This is the natural strategy for all of these frameworks. But what are some problems with this cutting method? The GPU is computing half tensors, and that is not conducive to saturating the GPU for matrix multiplication. GPU would so the half tensor, the shape might be irregular. So a full tensor might be rectangular, but if you cut it in 8 pieces, each one will be a stripe. So the dimension here, each one is thinner. That is why the GPU is not saturated. But the most important problem with tensor parallelism is that it has its own reduce operation that is super costly. And that is why when DeepSeek is being trained, they abandon tensor parallelism in the end because the communication is too costly. Therefore, only in inference do people use TP. But in training, they couldn't afford this cost, because in training you have forward and backward paths, and this O-reduce operation will impose huge cost. Does anyone know what O-reduce means? Awesome.
Can you repeat again, please?
Have anyone heard of O-reduce operation?
No, this is the first time I'm hearing.
Awesome. Yeah, O-reduce is one of the top 4 communication protocol, and is a highly interview question in AI software. So O-reduce means, for this example, if we cut a tensor into 2 GPUs, we have the first half of this tensor on GPU 1, and the second half on GPU 2. Then we go to another tensor and has the first half, the second half. This result in this D-shaped tensor. But since each of them only computes half of the computation results, they need to combine together. But if you have multiple GPUs, then you need to send the results to each of these GPUs. And the second GPU would also send its results, partial results, to all the other GPUs, and then do a combine. So reduce means combination. Therefore, how many communication are here involved? Each GPU go to all the other n GPUs. This is an n² operation, which for each token you need pass n² time, which is huge cost on the bandwidth. So how to solve this communication issue? So TP is too costly, tensor parallelism. Now enter expert parallelism, which is the hottest topic in 2025. What it does is it cuts the tensors not parallel, like vertically, but it splits them horizontally, which means each GPU would have the full tensor instead of only having half of the tensors. GPU 1 has 4 in this case, 4 full tensors instead of 8 partial tensors. So what is the benefit of this horizontal or vertical splitting?
Instead of half of them, maybe we'll be using the whole tensor per GPU.
Yeah, it's using the full tensor, and therefore it's better for GPU utilization, since it's a complete matrix, and each expert shape is often like D times 1024, whereas half tensor, the shape might be a very irregular shape. But the more important power benefit of expert parallelism lies in its communication. Since TP, it requires n² paths, Even if you use like sliding window passing, you would still need n pass. And n is the number of GPU, which can be 32 or 64 GPUs. So n is very huge. But for expert parallelism, you can reduce n squared communication into k number of communication. What is k here? K means the number of routed experts. So the number of expert might be 256 for DeepSeek, and the k will be 8 because only 8 of them are activated. And your GPU can range from 32 to 64. So n is very big, whereas k is small. And the expert parallelism, all to all, only let you to reduce n squared to k. And why? Because every token here only needs to be routed to not all of the GPUs, but only to those top 8 GPUs, or even less if 2 of them are on the same GPU, so less than k GPUs. And that's why the communication is very efficient. Any questions?
No, all good, I guess.
Right. Thank you for the response. So now, expert parallelism lets you reduce the memory bottleneck. So here is a interview question. Intranode versus internode. So what intranode means, it means within one node, one server, you usually have 4 or 8 GPUs. And this server, so what does a server mean? A server just means one GPU with some network card, NIC. And internode means you have multiple nodes. So multiple, those 8 GPU units. And the communication between those nodes are much more slower. One, because they are physically very far from each other. And also, their communication is CPU to CPU, because you need to go through either Ethernet or InfiniBand. Which is slower, whereas within one node, you can use NVLink, which is super fast. Therefore, tensor parallelism requires huge communication, right? N-squared communication. Therefore, it's only achievable within a node. So TP is intranode or internode deployment, if you are asked this question.
Intranode?
Yes, TP can only be intranode. Therefore, the TP size is usually 4 or 8. So for internode, you can use expert parallelism. Why? Because the communication is much slower, only k. So k is 8, whereas n 64 squared. This is too much bandwidth. Whereas EP, the bandwidth is low, So therefore you can have them more distantly. That's why only EP can go up to 32 or 64 or 72, whereas TP can only go up to 8 in realistic world deployment. Yeah, that's if interview question to keep in mind. The EP is so good and well. Are there any problem with it then? For example, if we have just 4 GPUs and we have 2, 5, 6 experts, then each GPU will need to store how many experts?
$64.
Yeah, thank you. Each one will have 64 expert. But is it only 64 expert? Or is it every layer we need 64 experts?
Every layer.
That's right. So for every layer, we need 64. But DeepSeek has 63 MOE layers. Or 61, or from about 60 layers. Therefore, that is a huge number of experts, right? And that causes out of memory really, really fast. And that's why normal EP or small scale EP doesn't really work in practice because there are so many experts. And the solution is WideEP or large scale EP. This is the most trending word, WideEP, which is used by DeepSeek, SGLane, all those popular stuff. So what does WideEP mean? It's just using more GPUs so that each GPU can have less expert on board. Instead of 2 GPUs, they can use 4 GPUs. So each one has fewer experts. And this elevated the memory pressure tremendously. But then, what are some problems with WideEP? Using more GPUs instead of fewer GPUs.
I think it's how to choose the experts per GPU.
Right on. So there are 3 problems, and one of them is how to set GPU experts onto GPUs. It's called this. There's a shuffling and a dispatch mechanism. And besides that, location of expert, what are some other problems? The first one is when you move from dense to sparse to this expert, one batch of tokens might be assigned to different experts, right? So one expert can have 3 tokens, whereas the other expert might only get 1 token. then the input shape is irregular. Whereas in the normal case, when you don't use mixture of expert, when you use a dense FFN, your input is all of these 6 tokens in a nice batch, a very regular shape. Whereas here, it's unpredictable what input size you will get, right, for each expert. Then what is the problem here? If you have a fixed input size, you can use CUDA graph capture. That means you pre-run a batch size, and then to make your kernel, pre-compile your kernel. What else? So when you divide into small expert blocks, each one of them won't be saturated. So GPU saturation is very low here. Instead of a neat matrix multiplication, you get 3, maybe vector matrix multiplication. So you can just use the massive parallel power of GPU to crunch them. So the GPU utilization is low. So how can we solve this low GPU utilization problem? Solution 1, group these irregular shaped tokens into one group gem, general matrix multiplication. And that will involve writing a custom kernel for this group gem. Therefore, TensorRT, TRT-LLM created a custom kernel exactly for these irregular shape format. So it diffuses all of these weights together and all of these small pieces together and performs a MOE group gem. So this group gem is a very important invention in the kernel level. And another way to solve this group gem, this irregular shape problem, is having more GPU, or should we have less GPUs? So will more GPUs have more irregular shape or less irregular shapes?
Just thinking.
I have a question.
Yeah.
So, here, even if you can have a group gem, you still cannot predict the number of tokens that get routed to this GPU, right? So it's group gem is only making it a little bit faster, but still cannot be pre-compiled.
Yes, you are right.
Gotcha.
Great question. So in the prefill phase, you can have like different lengths of input and different number of tokens. Therefore, you can't pre-compile this kernel.
But still, during decodes, also no, right? Because we're doing EP, and then this GPU has like maybe 8 experts, and then we don't know how many tokens are routed to this GPU during each iteration.
For decode phase, yeah, good call out. So although we can't exactly pre-compile, but we can do some optimization because decode is one token at a time, right?
Yeah.
So we will discuss that later on how we can optimize the decode.
Got it.
So that's a great catch. And back to this problem of irregular shape. So if you have more GPUs, then each GPU will have less blocks, less experts, right? So if more GPUs, you maybe have only one expert on this GPU. Then you won't have those small pieces. Therefore, more GPU is better, and that's why WideEP also alleviates the problem slightly. So problem 2 is what Koshki mentioned. It's about how to allocate the expert onto those GPUs. And are the experts balanced? So if you have 4 GPUs, the first GPU has this expert. So for each token, is it normally spread out among all GPUs? Or most tokens will be routed to only a subset of GPUs? It turns out that experts are super imbalanced. 20% of the experts handles 80% of the work. Like everything in life, the top 20 gets the top 80% of the GDP or something. And that's why in expert, top 20% or even less, top 2% of the experts will process all of the tokens. On the graph on the right, so each horizontal stripe means one layer. You can see that. So the expert numbers, so the top 10 experts get most of the tokens. And what is a problem for GPUs? If GPU 1 has expert 1 and 2, then all the tokens will be routed to expert 1 and 2, which goes to GPU 1. Whereas expert 3 and 4, they are called code expert. So those, and they don't get a lot of attention at all. So on the GPU side, how can we place those 4 experts, 2 hot experts and 2 cold experts, so that each of them can have a more balanced load? So should GPU 1 has both of the hot experts, or should it have 1 hot and 1 cold?
Like assigning them randomly, a mixture of experts.
Yeah, we want to mix the hot ones with the cold ones so that we don't get 2 hot experts here, so that all tokens will be routed to this GPU. The solution is we mix hot with cold So mix another hot with another cold expert. Therefore, each GPU will get a similar load. Does that make sense so far? Any questions?
A quick one. This applies to every layer, right?
Yes, for every layer.
So it
And
could be possible that for like basically in one GPU, it gets the different index of the experts for different layers.
exactly.
Got it.
Yeah, for layer 1, it can have 1, 3, expert 1 and 3. Layer 2, it has expert 50 and 61. So
Got it. Cool.
therefore, yeah, great question. So how can we choose how to place those experts per layer? So there are two options. One is to use one is called static placement of expert. So that means before we start the online workload, we use some historical data to see which expert gets routed most. In this case, using the historical data, we found this expert C and expert D are very hot experts. Therefore, we don't want to place them. We don't want to place them on one GPU, so we will swap them with one code expert on the other GPU. But what if the real workload is different from the historical data? Then should we use this dynamic load balancing, or should we use static one?
I think dynamic.
Exactly. So for Dynamo, we have a expert load balancer, which let you shuffle the expert weights even when you start serving online customers. So the static one will fix those expert location before the run, whereas the dynamic, we will see that after 5 or 10 minutes, these experts are very hot. Then we will switch those experts. But when should we switch and shuffle those experts? And the second question is, should we shuffle them per layer? Shuffle them per layer or shuffle them entirely together?
Per layer maybe, because we might have some hot like I think we might have some hot experts in in the GPU. So if we check per GPU, we can randomly assign different hot experts to different GPUs with the code experts.
You're right. The modern approach is per layer shuffling. So one layer, we will shuffle this. And then the good thing is, in the next iteration, we can shuffle the other layer, layer 2. And so in one iteration, we don't shuffle all of these experts, which is costly, but we only shuffle one layer so that the other layers can still be computing, right? The input X can go through this layer, whereas the top layer is being shuffled. Therefore, we don't need to halt the system to wait for 1 minute to shuffle them entirely. So this per layer shuffle can let us per iteration shuffle one layer. So the system don't need to halt at all, and users won't even notice. So SGLane, load balancer, EPLB, expert load balancing. The default config is this whole system shuffling. Therefore, when I tried it, after 10 minutes, the system suddenly stopped. You can't feed in any request. And why? It's because it's being shuffled. And that, what does that involve? It means transporting the weights through Ethernet or InfiniBand to other experts, right? And this will transport to this. If the network is slow, it will take a long time. And that's why if the system gets stuck, it might be because it's being load balancing. But TensorRT, TRT, LLM, and NVIDIA Dynamo, which is on top of TRT, uses this dynamic way, which you can read more in Dynamo or TensorRT. Any questions?
Yeah, I just have one question. So, you told that the expert parallelism works on uh, like infinite band or Ethernet, which has slow transfer in the weights, right? So, in that scenario, how do you optimize that? Kind of make it faster. What can be done to first? Since you told that you tried on XGLang EP load balancer and it stopped, so what's the solution to that?
Yeah, good question. So two solutions. You mentioned Ethernet is slow. So should we use a higher top K or a lower top K to reduce communication? A lower top K will mean you'll need to route to less instance. So a lower top K can help with bandwidth. And the other one is for expert balancing. You can use per layer method, per layer shuffling, instead of the whole system shuffling, so that less. So at one time there are less compute. Great question.
I have a quick question as well. So how long does it take to load the expert in one GPU, assuming from CPU memory to GPU memory?
How long does it take to load from CPU to GPU for one expert? So for the dense FFN, it's 65553, the hidden size. So it's a huge chunk tensor. And for the small experts, it's usually 1024. So that's much faster than the dense one. So for this redistribution, it didn't just take in 1 second or 2 seconds, but took me about 2 to 5 minutes for the 48 GPU deployment.
Wow. Wait, sorry. For this 2 to 5 minutes, do you mean the entire shuffling or per layer shuffling?
Entire system-wide shuffling. So that means all layers shuffle together.
Got it. Thanks for the clarifying that.
Yeah, great question. So if you like GPT online suddenly stops 2 or 4 or 5 minutes, that's unacceptable. So therefore, the load balancing is very important, right? The redistribution of expense. And you shouldn't do it very often. So maybe every 30 minutes or 1 hour. Okay, shuffle them. Good.
I just have one more question. Sorry. But how do you like evaluate? Like, do you use any NVIDIA insights or something to check the load?
Yeah, there is that's very important question. There's the balanceness metric, which is a number from 0 to 1. So it's usually 0.4 balanceness, which means each expert gets routed how much percent of the tokens per batch. And then you can read more about this in the TensorRT blog or the DeepSeek paper. So you can calculate a statistic on how balanced the expert is. Good question. So last point here is, what is the third problem of expert parallelism? So prefill and decode are different behaviors, right? In the prefill phase, you take the entire input batch, which can be like 1,000 tokens, the entire input, and multiply it with the weight. Whereas decode, you load 1 token at a time and multiply by the weight. So for prefill, we should, so in the mixture of expert, since the prefill shape, the input size might be different, right? If you have some requests are long, some requests are short, then you can't capture CUDA graph. Right, because you can't predict the input. So this is called normal. So for MOE, we should use normal dispatch, which doesn't capture CUDA graph, so it's normal. But for the decode phase, decode is very latency sensitive. Then for the MOE layer, you should turn on the low latency dispatch mode. And what does it do? It is tailored for generating output tokens during decode phase. And this mode prioritizes minimal delay minimal latency, and it supports CUDA graph. So it supports CUDA graph. However, there's a callout. It requires pre-allocating a fixed memory size for capturing the CUDA graph. So there is a drawback. Yeah, it's because in the decode, each request just have one token. Therefore, you can capture CUDA graph. You can say not capture one CUDA size, but you can capture size 4, size 8, size 64. So precompile all of these shapes of kernels. Then, if you have fewer tokens, you can use this size 4 CUDA graph. Whereas if you have like 8, you can use the bigger CUDA graphs. But for prefill, you can have a like 1024 with a 103. So it's hard to batch them together. Sure. Any questions?
Yeah, quick question. So what if we have CUDA graph captured batch size 1, 2, 4, 8, and then during one iteration we see a 5?
Then you can either chop it into one batch and then another one, or you can just don't use CUDA graph.
I see. What does Dynamo do currently?
Good question. So Dynamo is the kind of orchestrator on top of these engines. And within this engine, you have this MOE. So you can turn it on or off. Turn on the low latency to capture, or you can turn off the normal dispatch.
Got it. Thanks.
Good question. And that's how Dynamo is related to this different dispatch behavior. If you use aggregated serving, so one GPU has both prefill and decode, then you can't use normal. So you either use normal dispatch, which doesn't have CUDA, or you should use low latency dispatch that doesn't really work. So if you have one GPU that handles both prefill and decode, you can use any optimization here. And that's why Dynamo splits prefill and decode onto different GPUs. And then for prefill GPU, you can turn on the normal dispatch. And for decode, you can turn on the low latency dispatch. And that's how this system can achieve the highest throughput. The solution of Dynamo prefill decode disaggregation allows decode node to capture CUDA graph, whereas the prefill node lets use the raw input and let it handle the long input lengths. So that's why PD disaggregation is of tremendous value to expert parallelism. And that's why Dynamo is able to boost the EP to push it to another limit. Any questions so far? Yeah, so this is disaggregation, and the reason why MOE is being used recently is because we have this PD disaggregation, and that's why MOE can be performed efficiently. And that's why we are able to train big models like DeepSeek. And that's why Dynamo is very important to configure how many prefill and how many decode, and how to balance those experts among the prefill and decode nodes. The Dynamo has this SLA planner, which is on the high priority roadmap that lets you configure the number of prefill and decode nodes. So finally, as a bonus, do you think we should use more prefill or more decode in the WideEP deployment?
More
Think-
preference.
Or, why?
I think that the prefill part, that's where, like, I think we need more experts. The more workload will be happening in the prefill part.
Prefill, okay. The answer is usually, so for the DeepSeek deployment, DeepSeek v3, it used 12 nodes, and each node has, say, 4 GPUs. It is 2 prefill and 12 decode, a total of 14 nodes. Why? Which part has more latency?
It's decode.
Yes, decode is more latency sensitive because for each decode token, you need to load the entire context, right? So the entire context can be very huge. So the KV memory, you need to load a lot. And that's why for decode node, we have 12 decode and only 1 or 2 prefill. Therefore, we need to, so for decode is EP equals 48, and prefill is EP equals to 4. Okay. Any questions?
I want to ask, so we are having a lot of decode because DeepSeek V3 is a reasoning model, so conceptually is bottlenecked by the number or the amount of available KV cache size. Then hypothetically speaking, if we're looking at a non-reasoning model with MOE expert, where the output sequence length is significantly shorter than the input sequence length, then in that case, wouldn't we have more prefill with a higher EP parallelism size?
Good question. So the number of prefill and decode instance isn't always fixed, like 2 to 12. So there is this ratio, so PD ratio, that's, so it's either 0.5 or maybe 3.5. And what affects this ratio it depends on three things. First is model size. So should a big model have more prefill or decode? And the second is impedance versus output length. So if you have long prompts, should you have more prefill or decode? And third is about bandwidth. If you have a high bandwidth, should you have a higher PD ratio? And to answer this, our lecture 1 have had a deep dive, and I can send you the links if you want.
Okay, that would be great. Thanks. I wasn't there.
And that's exactly what Dynamo is important, because how many prefill and how many decode, we don't know. But Dynamo has some initiatives that can automatically do this. So hint, even linear programming, like solving this nice equation, doesn't suffice to solve this correct PD ratio.
I see. Are you referring to the AI configurator, or is it like a different planner thing?
For deciding the number of prefill and decode instance, you can check out this SLA planner in Dynamo. This is one component within this huge framework. Yeah, you
Got it. Got it. Thanks.
All right. Before we leave, any last questions or any topics you would want to cover next time?
Maybe how different inference engines help the models have better throughput or and less latency. I've been seeing a lot of new inference engines recently, the LLM cache and all this stuff. So just kind of interested.
All right, got it. Any other ideas or questions?
I also want to ask if it could be possible sharing, like, I guess, a bit more on the specific scenarios where disaggregation is better, like in terms of throughput, latency, or I guess both, or maybe we're sacrificing one for another.
Good question. I like that. Yeah, so when is disaggregated better than aggregated serving?
Yes, I mean, I don't know. I heard, like, generally, I feel like Dynamo is pushing disaggregation, but it seems like most of the cases where, I guess most for a lot of models, aggregation is still looks better in terms of throughput.
Good question. Very nice. Any other ideas? Suggestions? Oh, or maybe Jeff, are you working in this AI infra industry or more of the training inference?
I'm more on the inference side.
Okay. Okay, then we can focus on inference techniques then.
Yes, that's great. Thank you.
Yes, thanks for the great question. So thank you for joining, and let's reconvene next time.
Thank you for the session.
Thank you very much. Bye bye.
Bye.
Bye. I just have one more doubt. Is the recording stopped?
Let me